Hi everyone, it's week 9 and we're going to take a look this week at the sampling distribution of the sample mean, whatever in the world that means. Sampling distribution of the sample mean. What we're talking about is taking a population, in the particular case that we're going to do this week, which by the way happens to be problem 7.11 on page 293. What we're going to do is to analyze the time that patrons wait in line at a bank. The goal that the organization is 6 minutes, and they want to know are they in fact meeting that goal. Now, what we're going to do is sample the population being all people who ever come or might come to the bank to wait in line, and we're going to take samples of that population and calculate the mean. We could do that many times, an infinite number of times. And every time that we took a sample of, let's say, 100 customers, we get a new mean value, a new average value of waiting time. Now, obviously, we hope that they're all clustered around some number that's equal to or less than 6, but we can't expect to get the same number every time because we're going to take a random sample of 100 different members of the population every time. What we'll find if we plot out those average waiting times in a histogram is that it has a bell-shaped curve, or at least we hope it will, because that makes our life a lot easier when it comes to analyzing the situation. But that's what's meant by the sampling distribution of the sample mean. The sample mean is the mean that you get when you take a sample, and the sampling distribution means that those mean values will have a distribution all their own. And that's what we're going to work with in this chapter, this problem, and what we're going to really be working with a lot in the weeks to come when we start talking about hypothesis testing. And of course, we'll be revisiting our old friend, the normal distribution curve, z-values, and calculating probabilities based on the area under the normal distribution curve. Okay, so in this particular problem, again, we have 6 minutes as the goal. Now that's a goal. We don't know that it's 6 minutes, but we're going to assume for the sake of argument that it is. And we're going to see if we can prove or disprove that hypothesis by taking a sample of 100 customers. In fact, we've done that already. The folks that wrote the book did it for us. And they came up with a mean, or X bar, value of 5.46 minutes. That's the average time a person stood in line. Now that's less than 6. That's a good sign. But can we say with certainty that the real average, the population average, is 6? Or did we just get lucky and get 5.46 this time? Next time we might get 7 or 8. Who knows? So, but we do have another fact available to us, and that is after taking the 100 samples and running them through the formulas, we came up with a sample standard deviation of 2.47 minutes. And of course, we're going to use that as our best guess of what population standard deviation is. Okay, so the first question we have to pose is, what is the shape rather, of the sampling distribution of X bar, the mean value of waiting times? Well, if we knew for a fact that the population was normally distributed, then we'd know immediately that the sampling distribution is normally distributed as well. And that would make life real easy. But we don't know that. In fact, we have no reason to believe that it is normally distributed. Maybe it's more like a Poisson distribution. But whatever it is, we don't have to worry about that because we know that if we, according to the central limit theorem, if we take a big enough sample, the curve, the distribution curve for the sample mean will in fact be normally a normal shape, a bell-shaped curve as well. It doesn't matter what the shape of the original population is, as long as we take a big enough sample, that distribution of sample means will be normally distributed. And in fact, the book tells us that a rule of thumb is 30 or more samples. Now, there's nothing magic about 30. It's just someone's approximation rule of thumb. If you do this, you're safe kind of thing. It's no scientific calculation, particularly that says this is an absolute. It's just a recommendation. And in fact, this time we have 100, so we're in good shape there. So the answer to A, of course, would be central limit theorem. I'll just abbreviate here. N must be greater than or equal to 30, so we're okay. Now, if you were answering this problem for me in a homework assignment, you want to say a few more words so I know that you know what you're talking about. But that's basically what we're saying. Okay, the next question is what is the mean, the average value of the sample mean, and what is its standard deviation? Now, life is easy in the first case because the mean of the sampling distribution is the same as the population mean, 5.46. So there's no magic there. The really neat thing about this sampling distribution of the sample mean is that it gets smaller the bigger we make n. The bigger we make the sample size, the tighter the distribution for the sample mean becomes. If we have an n of 1,000, it's going to be much tighter than it is if its n is 100 and tighter than if it's 30. Of course, if it's less than 30, then well, bets are off because we're no longer guaranteed that it'll be normally distributed. So let's calculate it though for 100. The mean is equal to the population standard deviation. Again, we don't know what that is for sure. We're only guessing that it's about what our sample standard deviation was, 2.47. We're going to divide that by the square root, square root, SQRT, of, having trouble typing today, the number of samples, 100. So I'll click on that. And in fact, it's 0.247 as we could have done in our head because 100, the square root of 100 is 10. Divide that into 2.47 and we get 2.47 and we get 0.247. What if it was 1,000? Well, that would tighten up and we would have a standard distribution of only 0.08, so it would be very tight. If we only had 30, oops, wrong cell. If we had 30, I'll put that in up here, our standard deviation would be 0.459, twice as big. So 100's a nice number, we'll go with that. Okay, now comes the test. What's the probability? We got this value of 5.46 minutes. What's the probability of getting that? Something that value or something even lower than that value. We know that the probability of getting any individual number is 0. But what's the probability of getting that or some smaller number? Are we dealing with a fluke here, or a random, just got lucky and got that lower value, or is that something pretty common given the standard deviation of the sampling mean? Well, let's take a look. I'm going to pull this up here so we can see what we're doing. And I just happen to have handy, you wouldn't believe it, a normal distribution curve set with a mean of 6 and a standard deviation of 0.247. I was thinking ahead. Now, 5.46 you can see is way out here on this tail. So the area under this curve, this part of the curve in here, is going to be fairly small. But let's be a little more precise. What's the z value? I'll put z right here. Z, because we're going to use table 6.1 as we usually do. It's going to be equal to the difference between the value we're interested in, 5.46, and our assumed mean of 6, divided by the standard deviation of the sampling mean. Now remember, that's the number that we've just calculated by dividing the population standard deviation by the square root of n. That gives us a z value of minus 2.18. And if we flip back to table 6.1 and go to 2.1 on the minus 2.1 and then way across the 0.909 column, we get 0.0143. So 0.0143. And that's the probability that we're looking for. Okay, what does that really mean? And what can we conclude from this? Well, it tells us that the probability of getting a value of 5.46 or less, because remember, the table is giving us all the values to the left of the z value of 2.18 that we just calculated. And so that's the probability of getting something that low. So that turns out to be 1.43%. So do you believe that we were lucky and got 1 out of 1.43%, one of those cases? Or is in fact, should we really shift this whole normal distribution curve over, make the mean something a little bit less? Because it's, one chance in 100 or a little better is pretty slim. Typically, people like to see a 95% confidence level as being comfort zone. Well, we're at a 98.6% confidence level that the mean is 6 or better. So we can be pretty confident. If I were the manager of the bank, I'd say, okay, we've done it. We're better than 6 minutes by a little bit. Um, Mission accomplished. Okay, that's it for this week. Let me know if you have any questions. Uh, Keep doing the assignments. That's really the only way that I know to learn this stuff is to suffer through and figure them out for yourself. Okay, thanks a lot. We'll see you online.